What happens when you type something into ChatGPT? I bet you have no idea. Before we get into the details, let's look at what's happening from a high level. You've got your prompt, and this gets sent to something called a transformer model. This is the beating heart of all these systems. It's a large language model, and it doesn't matter if you're using ChatGPT, Gemini, Claude, they're all doing a very similar thing. The transformer model is the AI architecture that makes all of this work. And what the transformer model does is it creates a list of outputs. We're going to generate text one output at a time. And each of these outputs have a percentage chance of being selected. And these percentages change according to the prompt, according to the input. So we have this list of outputs, and we don't pick the top one. We roll a dice and we pick one according to the chance of it being selected. And in this case, we've picked the word here. And once we've chosen the word here, we add it to our input. And then we put the whole input, the original prompt plus the word here, back into the transformer model. That gives us a new list of outputs with a new set of percentages, and we do the same thing again to pick an output. This time we pick the word is. And we keep doing this. We generate one output at a time, put that back into the model, it generates the next output, and so on, until we get the nice responses, which you will see. But how does a transformer model go from the prompt to this list of percentages? Well, let me show you. So the first thing that happens is the prompt gets split up, not into words, but into something called tokens. Tokens are very similar to words, except there's not quite so many of them. In English, you have about 500,000, 600,000 words. There's new names, new phrases coming out all the time. Tokens, there's about 50,000 or 100,000 tokens. It depends on the model. Different models, like ChatGPT or Claude, use different ways of breaking things up into tokens. So sometimes they're the same as words, like I, love, and it in this example. Sometimes if the word in the prompt doesn't exist as a token, like GPT-5 here, it gets split up. Here that gets split up into 3 tokens, GPT, the dash, and the 5. And the thing that happens after that is for every token, there's a set of numbers, a list of numbers, and this is called an embedding. Here, I've just given some examples where there's only 4 numbers in each list. In practice, there's a lot more, hundreds or even thousands. But for every token, it has a set of numbers associated with it, and that's what the model's going to use to help produce this list of percentages.
A quick side note.
So these lists of numbers, these token embeddings, can be a bit mysterious. So let me try and give you some intuition. Here I've got 4 words: cat, dog, car, and truck. And for each of these, I'm going to create a list of 2 numbers. Not 4, not 100s, just 2. And by using 2 numbers, I can plot them on a graph like this. And here, I really want dog and cat to be close to each other because they represent somewhat similar concepts in the real world. And the same with car and truck. They're somewhat similar, so I want them to be together. And you might argue that cat is about as far away from car as dog is from truck. So I want to capture that relationship too. And that's what these embeddings are doing. Even if they're really long lists of numbers, they're trying to capture the inherent relationship between words that we know about. Now, on this page, we're only using 2 numbers. So we say the embedding size is 2. In the video, we're using 4 numbers. It just helps us explain things as we go along. But if we look at GP2 model, the medium model had 1,024. So it had a lot of numbers that were representing every token. GPT-3, the Da Vinci model, had just over 12,000 numbers. And GPT-5, they haven't published it, they haven't released the number yet, but there's many estimates that it's around 20,000 numbers. So each of these tokens have a long list of numbers, and these lists of numbers have been created to try and give some general information about the relationship between tokens.
Now, back to the video.
So once we have our token embeddings, we add to that another list of numbers called positional embeddings. Here, I'm not showing the numbers, I'm just going to show colored blocks from now on, because having all these numbers on the screen will be confusing. But again, it's just a list of numbers, the same size as the token embeddings, and somehow it represents how that word influences the rest of the words, given its position. So it doesn't matter what the token is, it's just saying if you're in position 1, this is the list of numbers. If you're in position 2, this is the list of numbers. And these two get added together, and that gives you a final list of numbers the same size for each token. And this is something called an input embedding. This is what the transformer is going to take as its input, and it's going to start to manipulate this list of numbers to help produce this final list of percentages. So after all of that, what we have is a set of tokens, GPT-5 I love it. And for each of those tokens, there's a list of 4 numbers. That list is different for every token, and it depends on what the token is and the position it is in the prompt. So I'm going to introduce a new concept here, and it's the notion of weights. And the weights are the parameters of the model. You might hear people saying it's a 7 billion parameter model or a 100 billion parameter model. Well, these parameters are just weights, they're just numbers. And this is where the magic happens. By learning good weights, good numbers, then it gives the models the capability to produce these good lists of percentages, which produces all the fantastic output we see. So here I have something called query weights, and there's 8 of them. So these are 8 numbers. And what we're going to do is we're going to take the token GPT, we're going to take the 4 numbers that are associated with that token, this input embedding, and we're going to multiply it by these weights. And what that does is it will give us 2 new weights for that token GPT, which are the query weights for GPT. And what happens is when you take these 4 weights, you multiply it by this 8, you get 2 new ones. Trust me, it's just how the math works. So we're going to do exactly the same thing for the dash. We take the list of 4 numbers, the input embedding, we multiply it by the query weights, and that gives us 2 new numbers for the dash. And we do exactly the same thing for all of the other tokens. So we now have a new list of 2 numbers for each of our tokens, and these are going to be called the queries for each token. And we're going to do the same thing again. We're going to have something called key weights. Again, they're parameters. It's just a list of numbers. It's part of the model. And we're going to do the same trick with each of these token embeddings. So we get a new list of 2 numbers for each token, which we'll call the keys. And finally, we'll do it again. We'll have a new set of 8 numbers called the values. We'll take each of our input embeddings and we'll create for each token a new list of 2 numbers, which we call the values. So we're just multiplying numbers together to get these new lists out. So what do we actually do with these new lists? Well, let's start with the queries and the keys. And what we're going to do is we're going to multiply the list of numbers, which is the query for GPT, with the list of numbers, which is the key for GPT. And this will give us a single number. It doesn't matter how long these lists are. They could be 10,000 numbers long. We multiply all the numbers together in the different positions, add them up, and this gives us the sum. If you're in high school or you remember back to high school, this was called vector multiplication and a dot product. It doesn't matter. We just get a single number that says how related are these 2 tokens. And dark colors means the tokens are related, light colors means they're not. And then we do the same thing for the dash. We multiply the query for dash with the key for GPT and the key for dash. And we do the same thing with 5. We multiply the query for 5 with the key for GPT, the key for dash, and the key for 5. And the reason we're doing this, we're building this triangle as we keep going, is that you're only allowed to look at words that you've already seen. So GPT is the first word. There isn't anything else. So you can only multiply that query with itself. When you get down to it, it's seen all of the words. GPT-5, I love it. So it can be multiplied with everything. So we keep going. And here we see that between the word it, the query for it, and the keys GPT, dash, and 5, the color's slightly darker. And that means we're trying to learn that the word it in this sentence refers to GPT-5. GPT-5, I love it. As humans, we naturally do this. We can associate that it with the right object or the right subject. But for computers to learn, they have to learn the right weights to do this kind of associations. Different weights for those queries and keys would give different numbers, which would learn different relationships between the tokens. So that's all it's doing. These weights are trying to capture different relationships between the tokens. And in large language models, this is something called the self-attention matrix. But you don't have to remember this. And once we have this self-attention matrix, this grid of numbers, we multiply it by all of the values blocked together like this. And this gives us a new block of two numbers for each of our tokens, which we're just going to call the scores. And again, if you're in high school or you remember it, this is just matrix multiplication. So we're multiplying one block of numbers with another block of numbers, and it gives us a new block. And now we have two new numbers again for each of our tokens. And this somehow is the almost final output. It's giving new weights to those tokens depending on the position in the sentence, the original embedding, and all of these relationships between the tokens. As you can see, a lot of these new artificial intelligence technologies is just multiplying numbers together to get new lists from old lists. It might not be what you expect, and we're not quite done yet. So we started off with our original input embeddings, and this was a list of 4 numbers for each of our tokens. And then we used some query weights, some key weights, and some value weights to create a self-attention matrix, and we got a new list of numbers out for each of our tokens, but these lists were only 2 numbers long. While this process of going from the original embeddings and using all these weights to get this new list is called a head. And this is an example of one head, but we're going to use 2. So we're going to do exactly the same thing again. We're going to take our input embeddings. We're going to have a completely different set of weights for the queries, the keys, the values. They can learn different relationships between the words, so head 1 and head 2 can learn different things. It creates a different self-attention matrix, and it gives us a different list of 2 numbers, a different list of scores for each of the tokens. And then if we naively just combine them together, we'd now have back again 4 numbers for each of our tokens. But hopefully those 4 numbers would capture more about the relationship between the tokens and the meanings of the words.
A quick side note.
So just as we talked about different models having different token embedding sizes, different models also have a different number of heads. So in our example, the token embedded size is 4. There's a list of 4 numbers. There's 2 heads, and the head output size is 2. Each head is outputting a list of 2 numbers. In GPT-3 Da Vinci, the token embedding size is 12,288. That means they have 96 heads. So they have 96 heads, each with different query, key, and value matrices, all learning different things, different relationships between the same set of tokens. And the head output size is 64. In GPT-5, the numbers aren't published, but the assumption is it's around 20,000, the token embedding size. And this head output size of 64 seems to be the magic number. There's lots of reasons for this. People have tried bigger head sizes, smaller head sizes, they don't work as well. 64 is also an efficient number for machines to compute and to parallelize easily. So this 64 seems to be a magic number. So if you know the token embedding size, you can make a reasonable guess at the number of heads. So this is incredible. You have many, many heads, each learning different relationships between words or between tokens.
Now, back to the video.
And as you might have guessed by now, we're not just going to combine the output of these heads in a naive way. We're going to add something called a neural network, which itself has another set of weights. And what this neural network does is it takes in those outputs of the heads and it multiplies those lists by another set of numbers, another set of weights that it learns, and it combines and reforms them in different ways until it outputs a new set of numbers, a new list for each of the tokens the same size as our input embeddings. And we're going to call this the layer output. So we have our original embeddings, they go through these heads, do the query value thing to learn relationships between the tokens themselves. That gives an output, and then there's this neural network that recombines all those values into a smart way to hopefully get a new list of numbers that somehow captures all of the different relationships that we've learned so far. It feels like magic, and to be honest, it probably is a little bit. And we're going to call this the layer output. We go from an original list of 4 numbers for each token, and the layer output through the heads and the neural network gives us a new list of 4 numbers for each token. And in other models, that list of numbers would be much bigger, but again, we're keeping the same size between the input and the layer output. So this layer output, we're actually going to call layer 1 output, and I think you can see what's coming here. We're going to do exactly the same thing again, but instead of starting with the input embeddings, we're going to start with this layer 1 output. We're going to create 2 new heads. These have new query key and value weights. We do 2 heads, we put it through a new neural network with more weights, and that gives us layer 2 output. So we do exactly the same thing, but now we're taking the input from the last layer and creating a new set of lists of 4 numbers for each of our tokens, which hopefully will capture even more of the relationships between them. Different relationships this time. Not sure what they are, but they're doing something. And we're not going to do this just once. We're going to start with our input embeddings. We're going to push that through 1 layer, push it through a 2nd layer, and we're going to keep doing this process multiple times. In fact, maybe 12 or even more layers. And at the end of these 12 layers, we're going to get a new list of numbers for each of our tokens. But each of these layers and each of the heads within the layers is learning some kind of relationship between the tokens. And this is where the magic is happening. This is that's going to enable the AI model to learn these relationships and predict new tokens. So there's one final step, and that's after we get this output from layer 12, we put it through another neural network, which means even more weights. And neural networks might seem complicated, but they're just weights. It's just numbers that are being multiplied with the numbers of each of these tokens. They're multiplied, they're added together, which transforms them into a new list of numbers. There might be one neural network, there might be several layers. All it's doing is multiplying numbers. And then that network outputs a list of these percentages for every token. And we get a percentage for all of our tokens. So remember at the start we said we might have a vocabulary of 50,000 tokens or 100,000 tokens. We get a list of 50,000 percentages or 100,000 percentages. And then we roll the dice and pick the next token according to those percentages. And this is what's happening when you type something into ChatGPT. So in describing what's happening, we've talked a lot about weights. So how does the AI, how does the artificial intelligence learn all these weights? Well, you start with a lot of data. That might be data from all across the web, it might be from books, it might be from a whole variety of other data sources. And the way the model learns is it tries to predict what's in the data. So here's an example. Here's the first sentence about London from Wikipedia. And it says, London is the capital and largest city of both England and the United Kingdom. And what you do is you start putting this data into the model and see what it will predict. So here we say London is the capital and largest city of both. We give that to our model. We get this table of percentages out, and perhaps the model chooses pineapple, which is clearly wrong. And what we want to do is we want to adjust these percentages such that England is higher, the percentage chance of selecting England is higher, and the percentage chance of selecting pineapple is lower. So that's what we do. We adjust all of these weights. All of the weights in all of the neural networks, all of the keys, the queries, the values, all of these weights we adjust a little bit such that we push England higher as a percentage and pineapple lower. And we do this again and again and again. We put trillions of tokens potentially through the model. We run this millions, billions, maybe even trillions of times with different inputs and seeing if we can match the output. And this is why it's so expensive computationally. This is why these models cost a lot of dollars to train, because there's a huge number of multiplications going on here when you multiply and add all these numbers through all of the layers to get the output, and then you have to do the same thing to adjust all of these weights. But this is what's going on. This is how it's trained. It's trained to mimic all of the data that it sees. And as part of that, it becomes very fluent and it learns relationships between tokens. And because it's learning relationships in language, one would argue it's learning some things about the world. But how much of that is represented as the model in all of these weights and numbers is up for debate. And the second big part of how the AI learns all these weights is something called instruction tuning. And here you have a bunch of humans that create a set of tasks. This could be writing poems about cats in space. It could be creating social media marketing campaigns, whatever it is. They create a bunch of tasks. The model that's learned from all this data is now put against these tasks, just like when you prompt ChatGPT. And you see if the model's correct or not. There's another bunch of humans that say whether the output is good or bad, Or they may even write some model output. Here's what I wanted. And just like we adjusted the weights based on the training data of predicting the next token, here we adjust the weights such that the model gets better at the task. This is repeated lots of times. There might be lots of humans scoring lots and lots of outputs. And this is what helps the model follow instructions and be better at it. And this part is called reinforcement learning with human feedback, or RLHF. And the reason I mention it here is so important is that this became a big part of the initial success of ChatGPT, but it continues to play a major role. When ChatGPT went from GPT-4 to GPT-5 and Grok went to Grok 3 and Grok 4, some estimates were that the models were improved, but the amount of reinforcement learning with human feedback was nearly 10 times as much as the previous models. So there's a lot of value in giving the models this feedback and making it do more and more tasks. So it's an important part of how the AI learns. So I hope that helps you understand what happens a bit more when you type something into ChatGPT. It might surprise you, all of these different layers, and we're just multiplying lists of numbers together, but I assure you that's what's going on. It's not all that happens. If you want to learn more about that, then check the video link on screen and subscribe if you like. And if you really want to go deeper into all of these topics, neural networks, how these models work, what are better prompting strategies, then check out your AI guidebook. It's a full AI course aimed at everyone. Everyone should be learning AI. You don't want to be left behind. It's a full course. It doesn't require any math or any coding. We go through each of the concepts step by step in a lot more detail and a lot more slowly. So take a look.